Welcome, Math 13 students. Here is a lecture on the details of section 7.1. We'll have a couple of lectures here. The first lecture has to do with estimating a population proportion. That's the main goal of this section. There's a couple of other things we'll talk about tomorrow. Basically, our goal is to use a sample to somehow estimate a population parameter. And in this section, we are going to use our sample proportion, p hat, to estimate our population proportion, p. And this brings up a bigger issue. Really, the goal here is to work with a population with unknown parameters. In this case, it's the unknown proportion. And what we want to be able to do is to take our sample and extrapolate from that sample to the larger population. And this might seem a bit of a stretch. The sample, after all, will be very small in comparison to most population sizes. However, from section 6.4 and the central limit theorem, we know that if n is greater than 30, then our sampling distribution, and this will work for either the mean or the proportion, is approximately normal. And that is just vital here. In terms of the mean, the distribution will have a mean very similar to the population, and the standard deviation will be a bit smaller than the population standard deviation by a factor of the square root of n. And this also applies, as I say, to p hat and to p. Now, let's talk about how this actually works. First, I will note that if we have a larger sample, we have a better estimate. At the end of the day, my sample really just gives me some sort of logical or reasonable guess as to the population parameter. I'm going to talk about the barnyard that we've all visited when we were kids, and we remember Mama Duck. There's Mama Duck right there. What do we know about her baby ducks? Her baby ducks, they like to hang close to Mama Duck. Most of them do. On occasion, you might find a little baby duck far from Mama Duck. Oh no, don't get lost, little baby duck. But in general, if we see a bunch of baby ducks, we know that there is a mama duck close by. And it is highly unusual to be far from mom. Now, here's the way this works. The baby ducks are all the possible sample proportions for a given size of n. The mama duck, she's unknown. We really don't know much about her at all because we're really just going to have a single baby duck to look at. Look, oh, there he is. And we're going to count on the fact that my baby duck that I get, my sample, should be close to the real mama duck. And that's really the bet that we make with our inferential statistics. We count on the fact that my sample statistic will not vary much from the population parameter. That's because of the power of the central limit theorem. All right, let's leave the barnyard alone. And let me talk about some vocabulary. So if we wish to estimate a population proportion, I've got to define some very basic terms. First, the point estimate. This is a value from a sample that is used to estimate a parameter. So it's important to realize that it comes to us from our sample and it's used to estimate our parameter. We have a point estimate for a population proportion. That point estimate comes to us from our sample, and it is the p hat. That's that x over n. That is our point estimate, and it forms the basis of our educated guess. And I really need to consider this because since we only get one sample, there is a probability that my sample is close to that mama duck, that population parameter, but there's also a probability that it will be far. And the idea is to try to quantify these probabilities. And once I do, I can go ahead and construct what we call the confidence interval. That confidence interval, as I often abbreviate CI, is a range of values that is likely to contain the true population parameter. Likely to contain the true population parameter. And we need to know how confident we are in that particular interval. So we define something called the level of confidence. And this is a probability. And it is the probability that the confidence interval contains the true parameter. So we're going to end up with a range of values and a probability that the range of values is correct. And this level of confidence here is given by what we call 1 minus alpha. Alpha is a lowercase Greek letter. If I haven't used it already, I'm going to be using it a lot now. And alpha is the probability that the sample is far from the parameter. That's the probability. Alpha is the probability. 1 minus alpha gives us the level of confidence. And common levels of confidence are the 90% level of confidence. That means my alpha is 10%. The 95% level of confidence, which means alpha is 5%. And then the 99% level of confidence, which means the alpha is 1%. Now, what does all of that actually mean? Well, let me give you an example. I'm going to use this example as I go through the balance of the presentation. We're going to consider a coin toss. We're going to assume that the coin is fair. We're going to toss our coin n equals 100 times. So the point estimate that we have would be p hat equals x, which is the number of heads, because I'm going to be looking at the proportion of heads. That's going to feed into the construction of this confidence interval. So what that means, if I repeat this process a whole bunch of times, literally millions, or maybe even tens of millions of times, most of my confidence intervals will contain the true population proportion. And if we're counting up the number of heads, the proportion of heads that I get if a coin is fair should be 0.5, 1 out of 2. So most of these confidence intervals from a low to a high, a low to a high, a low to a high, will contain the true population parameter. Only a small few will miss it entirely. Most of the time, I get this type of interval. However, sometimes I get this type of interval. Can I tell? No, I can't. I have just one sample in one interval, and I'm betting on the probability that I get this sort of arrangement versus this. And that's the bet that we make when we build a confidence interval. So if I continue with this example, so let's consider tossing that coin 100 times. And we're going to suppose that my sample proportion is 0.48. In other words, that came from p hat equals 48 heads over 100 flips. So that's where we get the 0.48. So 0.48, that is my point estimate. Keep that in mind. That's kind of our starting point. Now, using the process I'm going to explain in a few moments, we develop a confidence interval. In this case, it's the 95% confidence interval. And that 95% confidence interval says that the true population proportion for the number of heads when we flip is somewhere between 0.382 and 0.578. So the estimate that I have is somewhere between 38.2% and 57.8% of my flips should be heads. That's my estimate. And I am 95% confident in that estimate. What does that really mean? Well, we like to say that the 95% confidence interval for the population proportion P is 0.382 less than P less than 0.578. And I will call out the P here. This is the parameter we are estimating. I made an assumption that my coin was fair. Maybe it wasn't. This is one way that eventually we might be able to say something about that. So that's really the way it works. And what we really mean by this is if, for example, I constructed 100 different confidence intervals with 100 different unique samples. 95% of the confidence intervals I constructed would actually contain the true parameter. About 5% would miss it entirely, and I would be led down an incorrect path as to the value of where that parameter might lie. But it's a bet. It's a bet we made, 95%. In other words, it's going to be a good estimate 95 times out of 100. Now, how does that estimate get built? Well, to estimate a population proportion, we use the Z distribution. And I'll remind you that the mean is 0 and the standard deviation is 1 for the Z distribution. It's a probability distribution. And the way it pans out or works is this. Because of the area under the graph is equal to 1, that's our proxy for probability, we have two critical values. One critical value upstream, if you will, of 0, and one critical value less than 0. That's because essentially I could be off in either direction given my estimate, my point estimate. I could be a little too low or I could be a little too high. So that level of confidence, that 1 minus alpha, this little bit of alpha is a little bit of area. Half the area, half the alpha is here in the right tail. Half the area, half the alpha is there in the left tail. And that is exactly how we refer to that. We have a right tail and we have a left tail. And we have what we call critical values. And these critical values are numbers that are on the border that separate the likely from the unlikely. I want to make sure that we have likely outcomes. And this is one way to go about doing that. Now, I'm going to go ahead and find critical values. I'm going to run through an example there, and then I'm going to go ahead and use that. So to find critical values, we need the level of confidence. That absolutely has to be given. So critical values for that given level of confidence of 95%, that means my alpha for this particular example is 5% or 0.05. The little bit of area in each tail, 0.05 divided by 2. Now, some of you that are good with numbers and quick with numbers will realize that that's half of 5% or 2.5%, and you can work with that. Otherwise, it's a little bit difficult, but don't worry, I'm going to keep this in mind. Now, my critical values in this situation are plus and minus 1.96. And to find those scores, I'm going to remind you of the material we looked at in 6.2 and in 6.3. We use the inverse norm tool to find values given areas. Now, these keystrokes are going to be quite important when we get to the second half of the material tomorrow. For now, I'm going to use them to find my critical values and review my keystrokes. So let me go ahead and share my screen. There we are. Get rid of you. Go away. Come on. There we go. All right, so as I say, we'll use the inverse norm tool, and I'm going to do this a couple of different ways. When I do it for our first time, I'm going to do it with my stat wizard on. Not all of you guys have calculators with the stat wizard that I have. Some of the earlier TI-84s do not have all of this capability. So I've got my stat wizard turned on. So second click gives me back to my screen, then I'll pick up my distribution key and find inverse norm here. So I'm going to give that little bit of area on the left or on the right, or what I could do is I could go 1 minus 0.05, and that gets that 95% that's right in the middle. I can have my mean as 0, my standard deviation of 1, and I will select center here. Paste that into my function, hit enter, and you'll notice that I have two distinct z-scores. I have a -1 and a +1. They're kind of symmetric, not just kind of, they are exactly symmetric, about 0. I will round to 3 decimal places, which is 1.960 or just plus or minus 1.96. So let me stop my sharing for the moment and realize that I've got a plus or minus 1.96 for my critical values, and I got that from my inverse norm. Now, I said I was going to do this calculation twice. So let me come back to my calculator. Let me clear you off. And if I put and turn the stat wizard off, as some of you will have to deal with, this time when I pick up my inverse norm tool, I don't see what I see. And this time I'm going to use area coming in from the left, very much like the binomial cumulative distribution tool we used in chapter 5. So I will type in literally 0.05 divided by 2. That's the alpha divided by 2. My calculator will do the math for me, make him earn his living. The mean is 0, standard deviation is 1, and I'll close off the parenthesis. I'll hit enter, and you'll notice I have the negative 1.959 and change, or negative 1.96. Now, I do not need to do a second calculation if I've been paying attention to the symmetry of my graph. In other words, once I know this critical value over here, symmetry lets me get this critical value over here. I just have to remember the guy over here is negative, and the guy over here is positive. So it's very easy to use symmetry to take care of a lot of that. All right, so I've got my critical value. Now, we're going to use that critical value to build what we call the margin of error. The margin of error. The margin of error is the maximum likely amount of error for a given sample and a given level of confidence. We use the letter E for error, big E, to indicate the margin of error. We have a very specific formula to calculate the margin of error when we estimate a population proportion. The margin of error is equal to that critical value times the square root of p hat q hat divided by n. The critical value comes to us from our z distribution, This bit of detail comes to us from our sample. And it's important to realize that the construction of this is very, very similar to the construction of the variance or the standard deviation, I should say, when we were looking at the central limit theorem. I'll let you compare the formulas. If you squint, they kind of look the same. So how do we use this margin of error? So to construct a confidence interval for a population proportion, first off, we've got to meet certain requirements. We need a simple random sample. We need something that follows a binomial distribution in terms of all those requirements. There are 4 of them. Fixed number of trials, that's your sample size. Independent trials, 2 outcomes, and constant probabilities. We also need at least 5 successes and 5 failures in that data set so it doesn't get too lopsided. Otherwise, the distribution doesn't do its job correctly. And it's really important to remember that the sample material is what the researcher brings to the party. Your calculator has no idea where numbers come from. So if you've got a good sample, a simple random sample that reflects your population, your estimate will be a good estimate. If you got a crap ass sample, something like a sample of convenience, oh, you'll get an estimate, but it won't be a reliable estimate. So once I've got that out of the way and I've made sure that we've satisfied the requirements, I will need my p hat, which is x over n. I will need my sample size n. Excuse me. Once I have p hat, then I can find q hat. I need that also. And I'll need my critical values. And I will use all of that to find my margin of error. Now, a couple of things about that critical value that I had in that formula. There were 2 critical values, but I didn't specify which one to use when I had my margin of error up there. It's usually the positive, but I want to point something out here. The formula for constructing the confidence interval begins with p hat, this guy right here. And what we do is we add and we subtract that margin of error to the p hat. So it's p hat plus or minus e, which looks like, in terms of a formula, p hat plus or minus the z alpha over 2 times the square root of p hat q hat divided by n. And this will build the confidence interval. Stuck flat in the middle is the parameter we wish to estimate. It always goes from less than to greater than to greater than. Don't mess those signs up or you'll be wrong. So that is the way we build our confidence interval. Now, a little bit about this before I begin my example. I am going to run through the formula material one time. Then I'm going to show you the secret set of keystrokes that all the professionals use to construct their confidence intervals. Believe me, we don't really use this formula directly. It's all built into our calculator and everything. So we're almost ready to find that out. But we've got to look at one example so we've got something to compare our tool to. So here's my example. We're going to go back to that flipping of a coin 100 times. We have 48 heads, and we're going to construct the 95% confidence interval for the true proportion of heads when I flip that coin 100 times. We've already done some of the work. We found our critical values of plus or minus 1.96. I know what my p hat is. It's x over n. We're looking at the number of heads. So 48 divided by 100 is 0.48. That means q is 0.52. Remember, p hat and q hat have to add to 1. For my margin of error, I'm going to pick the positive 1.96. And then, of course, my sample size is 100. I'll need that formula too. So these are all the things that we need for our formula. So let me go ahead and get that plugged into our formula. So we have p hat plus or minus the z alpha over 2 times the square root of p hat q hat divided by n. You'll notice here I've got those various values in here. Here's that plus and minus. That's why I had two critical values, and here they are in action, one positive, one negative. So that was my confidence interval that I introduced before, but let's go ahead and run through those keystrokes on my calculator. We're going to do this one time, then we're going to verify this outcome using the dedicated confidence interval tool. All right, so we had 0.48, and I'm going to do the subtraction first. 1.96 times, I'll pick up my square root. Now there can be issue with order of operations, but honestly, there are none here. I'll just type in 0.48 times 0.52 divided by 100. And the order of operations ensures that we calculate the numerator and then divide by 100. So that's my expression. There's a 0.382 and change. Now, I need to redo this calculation with a plus there instead of a minus. I will use second enter to bring up that last set of keystrokes, and then I can modify that last set of keystrokes by changing the minus to a plus, and there's the 0.578 rounded to 3 decimal places there. So those formulas definitely work. They're not even hard to use really on a calculator like this. But again, that's really not how we do things. But before I leave this page entirely, I want to talk about our statement here. We are 95% confident that 0.382 less than p less than 0.578 contains the true value. That would be the true value of what? Of the population proportion p for the number of heads when you flip coins over there. Now, let's talk a little bit about presentation here. If I put this on a number line, my point estimate, p hat, lies right here, smack dab in the middle of my confidence intervals, right there. And what do? I add and subtract a little bit. That little bit is that margin of error. So if I need to calculate my margin of error once I've got my confidence interval, I can do that fairly quickly. Usually I pick the high value and then I subtract the point estimate, but I could use these two and get the same value. So there's a 0.098. So that's what we add and subtract. 0.098 minus 0.098. That's what's added and subtracted to my point estimate p hat. This enables me to present my confidence interval in the p hat plus or minus margin of error format. And this is the way we like to present things in the land of science. We do not usually use this type of format. We usually use this little guy right here. So on occasion, you'll be required to take your calculator output and rephrase it as p hat plus or minus e. So at the end of the day, that runs through all the keystrokes for the longhand version. Now, let me go ahead and show you where the TI-84 tool lies. We use what we call one prop z interval, or one prop z in. That's the tool we use. So let me run through this calculation, share my screen, and then I'll write a couple of things up. We'll be done. Now, these keystrokes work regardless of what version of the TI-84 you have. So having your wizard on or off matters not here. But we go to the land of stat. Oh, that's not the land of stat. There we are. And we're going to go over here to tests. So from here on out, we're going to spend an awful lot of time over here in the land of tests. And if I scroll down, I find one prop Z interval. That's the tool I use. You'll notice I can type in my X, I can type in my N, I can type in my level of confidence and calculate that directly. So there's a 0.382 less than P less than 0.578. And that is really the way we go about doing it. A couple of issues with this, and I'll jump back here in just a moment. You need to be a bit careful here. You don't want to confuse with one prop Z test. We want one prop Z interval. One prop Z test, this is section 8.2. We're not there yet. We will be, and we will use it, but just not today. So that can be a little bit confusing. So let me jump back over to my calculator. And I've just seen students make this error a lot. I asked for a population proportion estimate, and the student will accidentally see the one prop Z and go right there. And you'll notice that this screen has an awful lot of stuff on it that I've said not a darn thing about. So at the end of the day, that should be a clue that perhaps you've wandered off the path and you're not in the right place. If I take a look at the one prop Z interval, I see I have a space for an X, I have a space for an N, and I have a space for my level of confidence. That's really all that is required to build this confidence interval. I mean, you get your P hat, you get your Q hat, you get your critical values, you got your N, you've got everything you need. You've got your point estimate. And let me just point this out one last time before I leave it alone. When you do run through this material, you actually get a look at the point estimate P hat. So, as I say, don't confuse the one prop Z interval tool with the one prop Z test tool. We use them both, but we use them in different places. This is what we use in 7.1. That's what we used in 8.2. So for the next week or so, it's the one prop Z interval. Then you'll start to need to keep it straight with the one prop Z test. That pretty much brings my discussion here to an end on the first half of the material in 7.1. I'll have a second half of material on calculating sample size tomorrow. So please tune in and we'll see you then. Thank you and goodbye.